today we will start with a new topic which is thin film dynamics. So, thin film dynamics is a general, or it refers to a general class of problems where you have a liquid film formed which is sufficiently thin as compared to other relevant length scales of the problem. So, for example, in micro scale flows or even in nanoscale flows, sometimes you may have a thin liquid film, the thickness of which is much smaller than the characteristic geometric dimensions. So, there could be many such situations. For example, you can think of a problem called a spin coating. So, you have a liquid which needs to be coated on a surface. So, this liquid is spun on a disc and then there is a thin liquid film which forms on a surface, the film spreads radially outwards because of the rotational effects. So, in this way there are many such situations where you can actually use a technology of a thin or the science of a thin film formation and dynamical evolution of a thin film to understand the motion or to characterize the motion or even to develop new applications. For example, you can use thin film dynamics to understand the application of the spreading of a thin liquid film under the application of electric field, which is a very important consideration in modern science and technology, where electric field combines with fluid dynamics to solve some outstanding problems. So, it is quite important therefore to understand how a thin liquid film forms and dynamically evolves on a surface. Now, we will start with something which we have already discussed earlier, and that is a special thin film dynamics problem. So, where you have an inclined plane with an inclination angle of theta and a thin liquid film of height h. I am not committing at this moment whether this height h is a constant or it is a variable. That is the key to my discussion. For the time being, we are assuming this height as some height h, and the only constraint that I am putting here is that this h is much less than the length. Okay. So, that defines it as a thin film. Imagine a corresponding situation for boundary layer over a flat plate. Just I am trying to draw an analogy. So, you have a flat plate on which you have a boundary layer developing. This boundary layer theory that we use remains valid if delta by L is much less than 1, right. So, you can see that in some sense the delta in the boundary layer theory is equivalent to a length scale of h in the thin film, but there are interesting physical dissimilarities. In the boundary layer theory, we are talking about a very high Reynolds number flow, because the boundary layer is thin only when the Reynolds number is large. So, we are talking about a high Reynolds number flow in the boundary layer theory. On the other hand, we are talking about typically sluggish or low Reynolds number flow in thin film dynamics, although the thin film dynamics really does not bother so much about the Reynolds number. There are other forces which are equally or even more important, as not just viscous force and inertia force, surface tension force, gravity force, all these forces are also very important for thin film dynamics. So, Reynolds number alone cannot decide anything, but in most of the situations in thin film dynamics we are actually concerned about flow at low Reynolds number. So, what makes the thin film dynamics problem akin or similar to the boundary layer problem is not the Reynolds number, they are very disparate. The similarity is that despite the variations in Reynolds number, the difference in the magnitudes of Reynolds number in these two cases, what makes them similar is the separation of the length scales. This is the key, that is the h is the length scale which can be separated or be considered much smaller than the axial length scale. Similarly, here in the boundary layer delta is much less than L. Now, you have considered similar types of problems, or we have considered similar types of problems where you have a thin film confined in an environment in the context of lubrication theory. So, in the context of lubrication theory, when we have considered this, the major consideration follows from the fact that this is a rigid wall. In lubrication theory, this is also a rigid wall, this yellow line that I have drawn. So, this line may not be parallel to this, right, this line may be inclined in whatever way. So, this h is a function of the axial coordinate, it could also be a function of time, but it is a rigid boundary. That is the consideration in lubrication theory. In thin film dynamics, this is a boundary between two phases, say one liquid phase with another gas phase. So, if this is a boundary between two phases, then this is actually defined as a free surface. So, unlike the lubrication theory where it is a rigid surface, in thin film it is a free surface, and free surface will bring in its additional issues or complications, and that we will discuss as we move ahead with this. So, why I am starting with this problem is because we have solved this problem for a constant film thickness in case of a low Reynolds number flow or fully developed flow in the context of exact solution of Navier-Stokes equation, and we will start with that. We will not really solve that problem again, but we will formulate the problem and see that from that how can you graduate to a problem which is significantly more complicated, but essentially very similar. You have a free surface with a height h, and the key question is this height h may not be a constant. So, this height or the film thickness, the height what I am talking about as height is actually the film thickness, which can be variable. And in fact, in thin film dynamics the general scenario talks about finding out this h as a function of x and time, where x is this coordinate. Okay. So, let us set up the x axis and y axis like this. So, we will set up the continuity equation. So, let us assume that it is a 2-dimensional incompressible flow. So, the continuity equation x momentum. So, before understanding the significance of x and y, it is important to recognize that gravity is vertically downwards, that is what we are considering for this problem. So, we have the x momentum equation. So, we will quickly do an order of magnitude analysis, very similar to the order of magnitude analysis that we do for boundary layers. So, order of magnitude of this, let us call this as UC by LC. So, this LC is same as this L, what is defined in this problem. For any other problem LC could be something else, but at least in this example problem this is the characteristic length scale. So, question is, and a very important question is, what is UC, right? What is the characteristic velocity? In a boundary layer over a flat plate, you already have a predefined characteristic velocity which is u infinity, the fluid which is coming from the free stream. Here we do not know what is UC, right. So, this UC is not known, but what is known is that that UC and VC are related through the continuity equation. How they are related by the continuity equation? First of all, let the order of magnitude of V be Vc and order of magnitude of the characteristic length scale along y is h naught. H naught is equal to a constant h if h is a constant, but if h is a variable, this h for example could be, so in a typical situation I can show some undulated interface like this. In that case some reference say length which is say h at say x equal to L or whatever, or average h or smallest h, whatever, some reference constant h you call as h naught, a reference constant h. So, because these two are having the same order of magnitude, for the continuity equation to be satisfied you must have Vc by h naught of the order of Uc by Lc. So, Vc is of the order of Uc into h naught by Lc. H naught by Lc, this is the key parameter for this thin film analysis that we call as epsilon, a small number. Actually the theory that we are going to follow in thin film dynamics is a generalization of, or rather a specialization of the general asymptotic theory in mathematics. And in mathematics, in asymptotic theory you require a small number based on which you make an asymptotic expansion. So, that small number here is this physical number h naught by Lc, which is epsilon, we call it small. So, this entire theory will fail if this number is not small, that we have to keep. So, if this film is so thick that it is of the order of this one, then we cannot use this theory. Okay. Then we will come to the momentum equation. So, this is Uc by Tc, order of magnitude, this is Uc square by Lc, this is Vc Uc by h naught. Okay. This is Pc by Lc, we also do not know what is Pc, but we understand that Pc is important. First of all, Pc has to be important in all problems. The reason is that this arbitrary shape of the interface can be sustained with the help of a characteristic pressure difference across the two sides, and that makes the characteristic pressure in this problem, where you have an arbitrary evolution of the interfacial topology, that makes this Pc as important, because it is the pressure difference across the two sides of the interface that allows it to sustain its not only the static equilibrium shape, but also its dynamical evolution. And this is of the order of mu Uc by Lc square, this is of the order of mu Uc by h naught square, and this is rho g sin theta. Now, I want to introduce a particular symbol or nomenclature in this particular chapter, because eventually we will be dealing with non-dimensional quantities. We will recognize the dimensional quantities with a dash with all the variables. So, because these are all dimensional variables, I am just writing dash with all the terms. Nothing to worry about this dash, the reason is that we will be using terms without dash for the dimensionless variables. So, now let us make an assessment of various terms. So, these are the inertial terms. So, first of all, what is Tc? So, there are different time scales which are possible. the natural choice of the time scale is convective time scale. So, Tc is Lc by Uc. So, if you do that, then clearly these two terms, they will become of the same order. This term will also become of the same order as these, because Vc is of the order of this Vc, you can substitute this one, Vc is of the order of Uc into H0 by Lc. So, if you do that, then this is also of the order of Uc square by Lc. In the right hand side, out of the two viscous terms, which term is not important? Out of the two viscous terms, clearly this is not important. The reason is that H naught is much less than Lc, and therefore mu Uc by H naught square is much greater than mu Uc by Lc square, right. So far you can see that striking similarity with the boundary layer theory, that like delta much less than L, you have H naught much less than L. Now we will arrive at a striking dissimilarity with the boundary layer theory. What is that? Now you compare the inertial term by viscous term. Inertia over viscous, okay. So if you compare inertial over viscous, inertial term is the left hand side. So all these three terms are of the same order, you can take any of the orders as the order of the term. So rho Uc square by Lc divided by mu Uc by Lc square, inertial term by viscous term. So this is rho Uc Lc by mu. Oh sorry, I am very sorry, H naught square, very sorry. So rho Uc Lc by mu into H naught by Lc square, right. Right. So then this term, so this comes from one Uc gets cancelled and we multiply and divide by Lc. So this is the so called Reynolds number of the flow based on the characteristic length scale Lc. Reynolds number we always define based on the characteristic length scale, not on H naught, characteristic length scale of the problem. So then it is the inertia by viscous force, which is Reynolds number times H naught by Lc is epsilon. So epsilon square. So because epsilon is a small number, epsilon square is also supposed to be very small, in fact smaller. So when epsilon square is much less than 1, your intuitive expectation is that even for a moderate Reynolds number this will not be very large, and therefore for most of the thin film problems, although it is not mandatory, but it is customary that under all practical circumstances the inertial effects are not considered, until and unless the inertial effects are so important and so dominating that they have to be considered. So please do keep this concept in mind. The thin film dynamics does not tell you that inertia effect has to be neglected. It has nothing to do with the formulation of the thin film dynamics, but under most practical circumstances where thin film dynamics is applied, the inertial effects are neglected. So, that is why we will go ahead with the formulation with the inertial effects being neglected. So, once we neglect the inertial effects, the governing equation boils down to a very simple scenario: 0 is equal to minus del Similarly, the y momentum equation, so because the inertial effects are anyway not important, they are not important along x where the predominant motion is taking place. So, forget about inertial effect along y. If you want, we can still write just for the sake of completeness. Right. Okay. So, order of magnitude wise, let us write the various terms. Left hand side we will write only one term, because we have seen that all these three terms will eventually have the same order of magnitude. So, let us write order of magnitude of this term UC Vc rho UC Vc by Lc, and out of these two, which term will be important? X length scale is much larger than y length scale, therefore this term will be important. So, this will be of the order of so inertia by viscous for y momentum. Is of the order of rho UC Vc by Lc divided by mu Vc by H naught square. So, this is of the order of, you can get Vc cancel, rho UC Lc by mu into H naught by Lc whole square, right. So, in this case also you can clearly see that the inertial and the relative inertial and viscous effect, they are such that inertial effects are much negligible as compared to viscous effect. Now, so we can leave the inertial effect apart. Regarding the viscous effect, so the big question is, we have considered this term to be more important as compared to this term, right. That is what this inertial by viscous tells us, that inertial is negligible. So, this term is the highlight. Now, is this highlight itself a significant highlight? So, this term is of the order of mu Vc by h naught square. Its corresponding x momentum counterpart is mu uc by h naught square. These are the orders of this and this. Sorry, I am very sorry, where it is this. Okay. So, that term which I have circled here is of the order of mu uc by h naught square. Its corresponding y momentum term is mu vc by h naught square. So, their ratio is vc by uc, and as per continuity equation this is of the order of h naught by Lc, that is epsilon, which is much less than 1. Therefore, the moral of the story is that y momentum equation, of course the inertial effect is much negligible as compared to viscous effect, the viscous term itself is also negligible. So, that means in the y momentum equation you are left with only the pressure variation and the body force. Finally, we need to discuss one point before we close this particular lecture. What is this PC, right? So, this piece we have seen, we have discussed that UC depends on the physics of the problem. It is not like a fixed U infinity for the boundary layer over a flat plate, but PC, that is also another variable, another unknown variable. So, what is the relationship between PC and UC? So, for that we need to appeal to the x momentum equation. Remember, these inertial effects are gone. This is a dicey force, because if theta becomes 0 this is gone, right. But what always remains, it's this term and this term. These two terms will always remain. This term may or may not, depending on theta. So, we can arrive at a scale of PC by equating the scale of this with the scale of this. Okay. So, that means you can write, so this is a free space we have to write, PC and by LC is of the order of mu UC by h naught square, right. So, that means we can write PC is of the order of mu UC by h naught square LC. Okay. So, what we can write from here is PC of the order of mu UC by epsilon square LC, because h naught square is epsilon square into LC square. So, that one LC gets cancelled out. So, PC becomes this. So, you can see that the pressure is so important, because the pressure scales with 1 by epsilon square, and epsilon is a small number in this particular problem. So, to summarize, we have arrived at a pressure scale which depends on the velocity scale. Velocity scale depends on the physics of the problem, and we have arrived at the governing equations of continuity and momentum. We will take it up from here in the next lecture. Thank you very much.